Well, we derived Gauss's law, so the next step is to apply it to certain kinds of systems. As you'll see, Gauss's law makes the solution of certain electrostatics problems very easy. On the downside, Gauss's law is really only useful as a practical matter when you have systems of a high degree of symmetry. Last time around, we looked at the electric field due to a charged conductor, a sphere that bore uniform charge density, surface charge density, sigma. And as you saw, there were a lot of steps involved, and of course, when you have more algebra, there's a greater chance of making a mistake. At the end of all that work, we wound up with the fact that the electric field vanished inside the sphere, and that the electric field due to that sphere outside was basically that due to a point charge. And once you arrived at a solution, you might have gotten the feeling that, gee, maybe there was a faster way to get there rather than having to go through all of these steps. Well, Gauss's law does provide you with a faster way because that happens to possess a high enough degree of symmetry that you can use Gauss's law. So Gauss's law is the surface integral of the electric field dotted into the normal of the surface. And that's equal to 1 over epsilon naught surface integral over the surface charge density. The reason why I'm writing it this way is because we are dealing with the surface charge density as opposed to a volume charge density. And we'll assume that our sphere has radius r, capital R, and charge density is just sigma. So the next question is, where do I begin? Well, you want to pick a Gaussian surface. Now, there's an infinite number of ways you can pick a surface, but there are only a few ways that make this problem easy to solve. So you want to pick a surface such that you can pull this electric field out. In other words, so the surface over which you know that E dot n is constant. And if I look at this problem, it's a sphere, so it makes sense. Maybe I should pick a sphere as my Gaussian surface. I'll just sketch in a little dotted line in the middle there. Doesn't matter where I draw it. Inside, just so it's concentric with the sphere and it has radius r. What do I know about the electric field? Well, it goes over 1 over r squared. So therefore, my electric field is going to be constant over this surface. So I can pull the E out, and the surface area of this interior sphere is just going to be 4 pi little r squared. On the right-hand side, what charge is contained within that sphere? Nothing. So I just wind up with the result that my electric field vanishes inside this conducting sphere. Now, compare this and contrast this with the amount of work required to find the electric field using this expression. Certainly a lot less work. I could write this answer down immediately. If there's no charge contained within the Gaussian surface, the electric field, electric flux vanishes. It's as simple as that. Now, what about outside the sphere? I'll just pick a Gaussian surface that's concentric with my conducting sphere. And again, it has radius, we'll call it r. And I know that my electric field is going to be constant over that surface. So that'll give me an E 4 pi r squared. Basically, I'm just pulling the E out, just calculating the surface area of that sphere. On the right-hand side, I have 1 over epsilon naught There is charge within that Gaussian surface, so that just can be pulled right out because it's constant. And I have a surface area of my conducting sphere. Remember, when you're calculating this, this is where the charge is. It's not little r. This is going to be capital R. So this is 4 pi capital R squared. Sigma is just equal to Q over 4 pi capital R squared. It's just a certain amount of charge Q distributed over a sphere of radius capital R. So therefore, we wind up with the magnitude of E is equal to Q over 4 pi epsilon naught R squared. And we made use of the fact that we knew the electric field was in the radial direction. So again, compare this with the amount of work that was required to solve this expression, and you see it's much, much faster. So the rule is that whenever you have a sphere and you want to pick a Gaussian surface, it's also a sphere, and pick it inside, outside to determine what the electric field is inside or outside. The other problem that we discussed briefly, but was one that you probably worked through, was to calculate the electric field due to a uniform charge distribution and a uniformly charged sphere in particular. So now we have to deal with rho. And once again, I need to pick two surfaces to investigate the interior solution and also the exterior solution. Because we know the symmetry of this problem, we know that the electric field is going to have the same magnitude at equidistant points, and we know that the electric field is going to be pointing radially outwards from this. So on the left-hand side, I choose a Gaussian surface of radius little r. On the right-hand side, I'll wind up with 1 over epsilon naught rho. And remember here, you've got to integrate only over the charge that's within this, within your Gaussian surface. I've picked a Gaussian surface that's inside the sphere to give me the interior solution. So over here, I'm going to be integrating not from 0 to capital R, I'm going to be integrating from 0 to little r. And therefore, the volume contained within this little Gaussian surface is going to be 4 pi little r cubed over 3. And therefore my solution is that the electric field varies linearly as the distance from the center of the sphere. The only place the electric field vanishes inside is at smack dab in the middle, which is what you'd expect because you have equal amounts of charge all around that specific point in space. I'll make this a vector quantity because we did make use of the fact that the electric field goes out in a radial direction. Writing this in terms of charge Q rather than the charge density. My electric field is Q little r in the r direction over 4 pi epsilon naught capital R cubed. So notice this doesn't blow up. We'd have a problem if it did. Again, the only place it vanishes is right at the center of the sphere. And let's calculate the electric field outside. I'll construct another Gaussian surface, and I'll call it radius r once again. On the left-hand side, of the sphere, or on the left-hand side of this expression, I wind up with 4 pi r squared times the electric field. On the right-hand side, I have 1 over epsilon naught, and this time I'm just integrating over where the charge density is non-zero. It only is non-vanishing up to the radius of the sphere, capital R. And that'll give me charge density times 4 pi capital R cubed over 3. But I know that my charge density is related to Q by this expression. So we have Q over 4 pi capital R cubed over 3, and therefore, left out of E there, E is equal to Q over 4 pi epsilon naught R squared, and again, we knew that was in the R direction. It's a remarkable result, and also with the previous example that we worked as well. Outside, when you have a charged conducting sphere, or you have a uniform distribution of charge, spherical, your electric field is the same as if all that charge were concentrated at the center. So that's kind of a strange thing when you think about it, that as far as the field goes, we can just replace this with a single point charge Q at the origin, and anywhere out there, you'd see the same electric field. In the interior region, of course, it's different. Here, your electric field varies linearly as the distance away from the center of the sphere, vanishing only at the center. And when we looked at the charged conducting sphere, the electric field vanished throughout the interior region. And that actually is a feature of conductors in electrostatics, is that the electric field vanishes on the inside. So remember, if you've got spherical conductor, draw a spherical Gaussian surface. And I want to emphasize again, these Gaussian surfaces aren't real surfaces. It's just a mathematical concept that's either encloses the whole charge distribution or it's inside the charge distribution. It's not a real surface. It's just enables us to calculate the field at certain points in space. Let's look at the charge, or the electric field rather, due to a uniform line charge. And since we just have line charge, let's write this as a line integral. And lambda represents our line charge density. So now the question is, what Gaussian surface do we choose here? Once again, what surface do we choose such that we can pull this electric field outside of the integral and just calculate the surface area of the integral? Well, what do I expect here? Well, if I have a very long charge, I would expect my electric field to be the same, have the same magnitude for all same points or equidistant points away from that line. You'd also expect the electric field to be pointing outwards. So the choice in this case is to choose a cylinder. A very long cylinder. So therefore, on the left-hand side, the surface area of that cylinder is just equal to 2 pi s times the length. We're going to say this is a very long wire that has length L. On the right-hand side, if I integrate over this total amount of charge here, it's just lambda times L once again. The L's cancel out. And I wind up with electric field is equal to lambda over 2 pi epsilon naught s. Now that's the same answer as we got before, and as you can see, with a lot less work. I made use of the fact that my electric field was normal, or extended radially outwards from the wire. So we'll just put a little vector sign over here and put a little s caret to indicate that your electric field's pointing out that way. Problem that we didn't solve last time around, but it's closely related to this one, is what do you do if you have a uniformly charged cylinder? So what Gaussian surface do I choose here? Well, once again, choose a cylindrically shaped Gaussian surface. And we'll assume that our cylinder has volume charge density rho. And I've got my interior surface and my exterior surface. Let's do the exterior one first. We'll assume that our radius is larger than r. And on the left-hand side, once again, we can pull our electric field outside of the integral. The surface area of the Gaussian surface is just going to be 2 pi s times the length. On the right-hand side, I can pull the volume charge density out because it's uniformly charged. Leaving me with rho pi r squared times L, where r is, again, the radius of the cylinder. It's my radius, and that's the point at which I'm evaluating the electric field. It's actually more useful to express this in terms of line charge density for comparison with the previous problem. Volume charge density is equal to Q over pi r squared L, or lambda over pi r squared. So another way of writing my electric field is just going to be lambda over 2 pi epsilon naught s in the s direction. So notice, just as with the sphere, when we had a uniformly charged sphere, it looked from the outside as if all that charge were concentrated at the center. Here, it looks like all the charge is concentrated along the axis. Now, how about on the interior solution? What would you expect there? Once again, you do have charge density, or charge rather, distributed throughout this volume, so you would expect to have electric field inside as well. On the left-hand side, once again, I can pull my electric field out, and the surface area of this interior surface is equal to 2 pi s times the length of the cylinder. On the right-hand side now, I can't write this as r squared because I'm not integrating out to the radius. I'm just integrating to some closer point, s. And putting in the vector notation because I know that my electric field extends radially outwards, and we did make use of it. So your electric field in the interior is equal to volume charge density times S over 2 epsilon naught. I'm going to leave it in this form because I want you to compare this with the expression we got for the electric field due to a uniformly charged sphere. Remember what that was? It's just E is equal to rho r caret, over 3 epsilon naught. So notice in both of these cases, it's proportional to the charge density, and in both cases, the electric field extends radially outwards. In the first case, of course, you want to think of it as being extending out like the rays from the sun. Out here, these electric field lines are radiating out from the axis. And notice you have a factor of 3 in the denominator as opposed to a factor of 2 for this particular problem. The point is, when you're looking at cylinders or wires, choose another cylinder as your Gaussian surface. If this cylinder had not been uniformly charged, but say been a conductor instead, what would you expect your answer to be? So now I've got a conducting cylinder as opposed to a uniformly charged cylinder on the other side of the board. What's my electric field going to be on the inside? It's just going to vanish. Why? Because any charge that exists is outside of my surface. So there's no flux going through here. So therefore your electric field vanishes. Outside, and we're going to assume that these ends are very far away. What you'll find is that the electric field goes as lambda over 2 pi epsilon naught s in the s direction. And once again, it looks from the outside as if all this charge, so it's concentrated on the surface of your cylinder, we're actually on the axis of the cylinder itself. Let's look at another kind of problem. We haven't investigated yet quantitatively, I should say, the electric field due to a charged sheet. So let's take that up right now. I want to determine what's the electric field above and below the sheet. We'll assume that it bears surface charge density, sigma. Question here is, what Gaussian surface do you choose? Before, with this, anytime you dealt with the sphere, you choose another sphere. If you deal with a cylinder, wire, you choose a cylinder. What do you choose here? Do you choose another surface that's infinitely large or very, very large that encloses this, or is there another choice? It turns out a good choice for calculating the electric field or making use of Gauss's law is to pick what's called a pillbox. So my pillbox straddles this region. It contains a certain amount of charge sigma within here, and we'll see that the electric field is going to be in normal direction to this plane of charge. If you'll remember when we were going through those examples of looking at the field lines and you had a whole collection of charges, what you saw is that as you bring charges, same charges together, same sign charges, the electric field lines tend to get pushed up, okay? So what you're going to have here is that your electric field is going to be pointing everywhere upwards from this surface and downwards from the surface. So in other words, the electric field lines go away because this is positively charged. What you would also expect is that at any point along here, same position above this charge sheet, that your electric field would have the same value because it's very, very large. So therefore, my electric field has value E, and this little area here we'll call A. The electric field's pointing in the same direction as the normal to the surface. Down here, your electric field pointing downwards is value minus E, minus indicating the direction. And the normal to the surface is also pointing downwards as well. So on the left-hand side, we have EA plus minus E times minus A. And over on the right-hand side, our surface charge density is uniform, so I can pull it out. And the area here is just A over epsilon naught. So now we wind up with another surprising result, that your electric field due to a charged sheet is just proportional to the surface charge density divided by 2 epsilon naught. And above the sheet, this is going to be positive. And it's going to be negative below. The reason why it's surprising that you get this answer is because you notice there's no dependence on the distance away from the charged sheet. So whether I drew my pillbox like this or I drew the top of it way up here, I wind up with the same value. And how can that possibly make sense? After all, the electric field goes as 1 over r squared. As you get further and further away from a charge, you would expect your electric field to get smaller and smaller. But that's not what we're showing here. And the reason why is because we're assuming this charge sheet is very, very large. And the way you want to think about it is that, okay, even though as you get further above the sheet, the electric field due to the charge that's immediately below you decreases, but then all this other charge is coming into view, if you will. So the surprising result is when you have the electric field due to a charged sheet, it doesn't depend on the distance away from that sheet. Okay. Now let's take what we've learned here and apply it to a more complicated problem. I mentioned that Gauss's law can only be used when you have systems of a high degree of symmetry. So what do you do if you have 2 charged sheets? And let's suppose we have positive sigma on the upper sheet and negative sigma on the lower sheet. How do I figure out the electric field above this sheet, in between these two, and below it? Well, what we can do is solve each problem separately and then make use of the superposition principle. So if I know what the electric field is due to this sheet, figure that out in each of the regions, and I figure out what's the electric field due to the bottom sheet, each of the three regions, I can just add those results up. So let's look at sigma first of all. So due to the sigma sheet on the left-hand side, the electric field lines point away. It points up above it and downwards below it. Forget about the presence of this sheet while I'm calculating the electric field due to this one, okay? So I know it has magnitude of sigma over 2 epsilon naught. I just figured that out. And minus signs, of course, indicate the direction. Now let's look at the charge or the field lines due to the negatively charged sheet. Electric field lines terminate on negative charges, so the electric field due to the minus sigma sheet up above it is going to be downwards. Now, forgetting about the sigma sheet, we're only dealing with the negative sigma sheet. Electric field's going to point towards the negative charges. And below it, the electric field lines are going to point upwards. So now I've written down what the electric field is in each of the three regions due to each of the sheets. All I have to do is just add them up. So above both sheets, the electric field vanishes. Below both sheets, the electric field vanishes. And in between, the electric field has value sigma over epsilon naught. And again, negative sign indicates direction. The electric field lines point from the upper sheet to the lower sheet. And once again, what you want to notice here is that the electric field will be uniform in magnitude and also is independent of where you are in between here. So if you're talking about a point here or here or here or here, it doesn't matter. The electric field has the same value between two infinitely large charged sheets or very large charged sheets. Now, last problem I'm going to do looks kind of difficult, and the reason why it doesn't look like there's going to be an apparent symmetry. So we did a problem where we looked at the charge distribution, or rather the electric field due to a uniformly charged cylinder. Inside of that cylinder, the electric field was equal to the charge density, volume charge density, times S over 2 epsilon naught and extending radially outwards. Outside, saw that the charge electric field is equal to lambda over 2 pi epsilon naught S in the S direction, and I did write this in terms of lambda to make it consistent with the notation I was using for a wire. Let's say now that I'm looking at this charge cylinder from the end, and I've punched a hole or tube through that cylinder. And that hole, or tube rather, is offset from the center by a distance b. I want to know what's the electric field inside of that hole. So just looking at it right now, there's no symmetry. Symmetry's been goofed up because of the tube that I've punched through it. But what I can do is to treat these two problems separately. So in other words, if I have my original problem of my uniformly charged sphere, and then I add to it another cylinder that bears equal magnitude of volume charge, but the opposite sign. So this is rho, and this is minus rho. So I'm going to figure out what the electric field is due to my original problem, add to it a cylinder that's offset by a distance b that has opposite charge. So if I add this to this, this part will cancel with this section right here, this volume right here, giving me what I want. So just need to write down the electric fields due to each of these. In this case, it's going to be rho s over 2 epsilon naught in the s direction. Over here, it's going to be minus rho over 2 epsilon naught also in the s direction, but I have to offset it by a certain distance b, because this is a distance b from the origin, or from the axis. And then my solution will be, when I add up the electric fields due to each of these configurations. So if I add this to this, I'll see that my electric field is just equal to rho b over 2 epsilon naught, where b is a distance from the center of this cylinder to the center of this one. So what looked like a very difficult problem to solve and something for which you might not think Gauss's law could be applied, turns out to be pretty straightforward. We just make use of a couple of things. We make use of the fact of the superposition principle, and then handle the simpler problems first, and then add everything up to get your result. So remember, whenever you encounter a problem in electromagnetism that seems very difficult, well, it's kind of party-core, but as it turns out, there'll always be some kind of trick that you can use to arrive at a solution. Basically, you want to make use of the symmetry of the systems a lot. That'll simplify things a great deal. And then also you want to make use of the superposition principle. You break harder problems, more complicated problems down into simpler problems, then you can arrive at a solution. So that concludes my talk on Gauss's law, and next time around we'll be discussing the electric potential.